and welcome to the another episode of the Global AI Summer Bootcamp conducted by the Innovation Tech Community. So here I am Pratap Reddy, the Microsoft AI MVP. So along with me is our expert speaker Aishwarya. So she's ML expert. So she is going to demonstrate about the non-coders guide to the machine learning, so we can have more insights from the Aishwarya so about how machine learning works in the day-to-day life and how ML plays a key role in IT industry and daily work life, and so there is how can we use this non-coders guide to the machine learning part and everything we can get some insights from the Aishwarya. So I would like to introduce Aishwarya. Hi Aishwarya.
Hey, hello everyone.
Hi. So how are you?
I'm doing good and I hope you all are doing good as well.
Yes, of course. And so we are lucky to have you a session about this global AI bootcamp. And so lots of enthusiasts are interested about your session. So probably 500 members are registered for your, especially for your event as well. And
Okay.
so yeah, we are looking for your more insights from you. And so are you ready to do a demo on this non-coders guide to the machine learning?
Yes, absolutely.
Yeah.
I'm ready. And can you confirm to me if you're able to see my screen?
Yes. I will share my screen. I will share your screen. Yes, it's now it's visible.
Okay.
Yeah.
Cool.
Yeah.
So I'll start right now.
Yes, you can.
Okay, cool. So thank you so much everyone for joining today. And today I'll be talking about, a non-coder's guide to machine learning. And why is this important? So one reason is that just from my own personal experience. So whenever I tried to learn machine learning in the past, I was really scared because it was full of, math and statistics and everything. But then I got into product management where I had to manage AI and ML teams. So I figured that, is if you learn it at a very conceptual level and at a more abstract level, it will make it very much easier for you to, learn the more complex part of machine learning. So therefore, this particular session is going to be for everyone who doesn't have much knowledge on machine learning, or maybe they're scared of it like I was, or people who are managers who work very closely with engineering teams and they need to know a lot about AI, ML, and data. So this is for you if you have not learned machine learning before. So this will be at a more conceptual and abstract level. So let's see what we are going to talk about today. So today we are going to talk about, like, how machine learning works and what are the types of different machine learning and when to use machine learning and when not to use. So, recently AI has become like a really big buzzword and everyone is becoming pretty obsessed with AI, but that doesn't mean that, AI is necessarily good for your startup or necessarily good for your team, because most of the AI solutions are very expensive, very time consuming, and they require, data scientists and engineers who are a bit more advanced. So, based on that, it's very time and money intensive. So, there are many occasions where you shouldn't use AI and ML at all, and it's good to use the normal coding algorithms. So, we're going to talk about that, and we're going to talk about challenges of modeling and strategies, and some of the common ML algorithms, and some of the use cases. So, this will be on our agenda for today. So let us first start as to what exactly is machine learning. So Arthur Samuel from IBM defined it as, the field of study that gives computers the ability to learn without being explicitly programmed. So till now, if you have learned a bit of programming, you will find that for each and everything, you need to sort of, write if-else conditions. You need to write loops and everything. So you need to tell the computer how it needs to calculate stuff. But when it comes to machine learning, you don't tell the computer how to do things. You just tell it that, hey, if this is the question and this is the answer, and you show it, 1000 questions with their 1000 answers, then the machine kind of like understands it on its own, and you don't need to explicitly program it. So therefore, you don't need to provide, exact instructions to solve a particular problem, and you can just show the examples of that problem and it will sort of figure it out on its own how to solve it itself. So just to give you, like, this section is like really really important because this is very basic. Because like, to give you an example, like if you have a small baby, so if you tell a baby how to recognize cats, so how do you teach that baby? You show it images of cats, in cartoons, in storybooks, in real life, and you point it towards that and say that, hey, this particular thing in the storybook is a cat, and the baby understands it on its own. So this is similar to what we how machine learning works. On the other side, if you try to teach a baby what a cat is by saying that, hey, a cat is something which has two ears and four legs and one tail and two eyes and many many other attributes, then first of all, that lists become very long. Those if else conditions become really really big. And moreover, there are many many animals which will satisfy that criteria. Or even dogs also have 2 ears and four legs and everything. So you see how teaching a baby what a cat is much easier, to teach it by showing it what a cat is, and then it starts to understand it's on its own. So that's how machine learning works, just by showing samples of what you want it to recognize. So here we will compare, what is machine learning versus what is traditional software. So traditional software sort of generates predictions by, you give it the input data and you give it some rules, and then the CPU works and give you the new outputs. Whereas in the machine learning, you give it an input data and then you give it previous outputs that, hey, these are 1000 images of animals, and there are the labels of those 1000 images. This is a cat, this is a dog, this is a squirrel, blah blah. And then the machine sort of understands it on its own and is able to generate new outputs from it. So this is the main difference between ML and traditional software. So for example, if you have a calculator on your desk, these days less number of people use a physical calculator. But in any case, suppose you have like a physical calculator, would you call it that it's like AI or something, or is it like machine learning? Oh well, I don't think so, because in the calculator you have defined all the rules. The rules are that a plus symbol is for addition, a minus symbol is for subtraction. So a calculator is an example of a traditional algorithm or a traditional piece of software, whereas a software to sort of recognize OCR characters or something, or a software to sort of predict what the weather will be or what the temperature will be in Bangalore tomorrow. Those kind of things are more on the machine learning. So we are going to learn a bit more about them and with more clarity. Okay, so first let's see what is the difference between AI and machine learning and deep learning. So, in essence, you can say that deep learning is just a subset of AI and machine learning. So, AI is a very broad concept. It has many, many different domains within it, and it's more like that. Hey, okay, how do you enable machines to perform, greater than equal to the level of the humans. So that's what artificial intelligence is, and machine learning is basically the methods and the tools which sort of help you realize the goal of artificial intelligence. So, and that's how you can sort of define it. And deep learning is an even more complex version of machine learning. I will, yeah, more specialized version, you can say, which use neural networks which have many layers. We're going to talk about that in a little while. But for now, just take a step back and think about it. If you are a human, you have how do you sort of take in information from the environment, and how do you process information? You see it through the eyes. So that is equivalent of computer vision. Okay. And then you hear sounds and then you speak things. So that is an example of text to speech recognition, or natural language processing. And then you also read stuff in the books and in the magazines on your computer. That is also what it falls in the category of NLP. And then you sort of move around, use your limbs and stuff like that. So that's an example of you can say autonomous or robotics. So all these are different forms of machine learning. And if you take a closer look at all of these, they all correspond to, one part of the other of how humans work and how humans absorb information and process it. So that is, in a sense, the difference between AI and machine learning. Okay, so let's see where, is ML something imaginary, or do we see it every day in our world? So you will see that we find ML at a large number of places. You will see it in this Amazon, in the shopping websites. You see a lot of product recommendations, even on Netflix, YouTube. So you see wherever product recommendations are, we have ML. Then in spam filters, the Google spam filter in the Gmail uses a lot of ML. And then mail routing via the OCR. So we saw, optical character recognition, where you identify, which characters or numbers are there in an image. That is also, machine learning, and also to detect credit card frauds. So in a large number of places, we use a lot of machine learning right now as well. Okay, so let us now understand, what are some of the data terms which, ML managers or people who are beginning in ML must know about. Okay, so let's see what first is structured versus unstructured data. With structured data, we mean that, data which is based on a predefined fields for each record, and they are sort of stored in relational databases. So MySQL or PostgreSQL is an example. And then unstructured data is where you don't have a fixed format of the data. It can be anything. It can be, images, videos, it can be sounds, text, links, and, animations or written text. It can be anything. It encompasses large formats of data. So these are the two main kinds of data. And if you take a look at this pie chart over here, so you will see that if you are working in a typical startup, for example, you are working in Meta, for example, or Google, then you will see that 80% of the data is unstructured, whereas only 20% is structured. So how do you, so like, for example, if you are, a product manager at Meta, for example, or at Instagram. So in Instagram, if you are, if you have to construct, the data architecture, you can say. So you will say that, hey, okay, if I'm a user and I'm logging into Instagram, then, my username, password, my country, and other my profile details, those kind of information is stored in the structured data. Whereas in the unstructured data, if you take a look at Twitter, for example, so in Twitter, if you take a look at the news feed in Twitter, you have different kinds of objects in the news feed, right? Sometimes people will put links, sometimes there'll be images in the tweet, sometimes there'll be videos, the text only, long threads, whatnot. So many different kinds of data. So all those big, large chunks of unorganized or unstructured data is what comprises a very big portion of, Twitter and Instagram and Meta and most of the organizations. So this is what we mean, first of all, by structured and unstructured data. And you can say that structured data is very easy to enter, search, and analyze because, it's all text and it falls into, clear buckets of things. Whereas to search an unstructured data or to do any sort of data analysis on it requires specialized tools. So this is what you should know about structured and unstructured data. Now, when it comes to the data which you commonly encounter in machine learning, so you have continuous, categorical, and discrete data. So by continuous data, we mean something, it's like, when we were little, we used to learn, right, about continuous intervals and discrete intervals. So this is similar to that. And like, for example, in continuous, this is the kind of data which can take in any value between, a set interval, you can say. For example, if I have to predict that, hey, okay, I know the temperature in Bangalore on May temperature in Bangalore since the past 10 years. Now I have to predict what is going to be the temperature in Bangalore tomorrow. So that is an example of continuous data. Where the temperature can be anything. 32.8, 35.4, anything at all. So that is continuous data. And then you have categorical data where there are finite number of categories and groups, and your answer will always fall under one bucket or the other. So for example, if you say gender, then there'll be a finite number of genders or certain specific categories of it. Or if you are enrolling in a university, then it will have finite number of courses, maybe 50 courses. So okay, computer science, mechanical engineering, botany, blah blah. So there'll be 50 of those categories. So that is example of categorical data. And then discrete data is the one which has a countable number of values between two values. For example, age. If you have to predict the age of a person or the life expectancy of a person, that number is always going to be between 0 to, I don't know, 110, because that's like the maximum age possible for humans and stuff. So that is an example of discrete kind of data. So these are the different categories of data. And then there is the time series data as well. So this is really helpful when it comes to, especially IoT devices. So for example, if you wear a smartwatch and that smartwatch is continuously monitoring your heartbeat every 5 seconds or something like that. So then that is an example of time series data, because all the data points are organized in the order of time and they are equally spaced by time as well. So these are all example of time series data. You can remember it by the smartwatch example. Okay, so now coming to the more ML specific terminology. So for example, I give you the problem that, I have, I will tell you that, hey, okay, this is, can you predict the pricing of a house, based on the existing prices of houses? So for example, you have these three houses over here, house one, two, three, then what will the prices of these houses depend on? It will depend on the neighborhood, first of all, Waycroft and Kerry Park. So, if you take an example of Bangalore, some houses will be more expensive than others. So for example, houses in Indiranagar will be more expensive than houses someplace else. So, it depends on the neighborhood a lot. Then, school district and the square footage. So bigger houses will be having higher price. Then number of bedrooms. So large number of bedrooms will be also a function of the house price. Which year it was built in? Is it very old? Is it relatively new? And this is the final output that, hey, okay, this is the selling price of this house. This is, I don't know, maybe 70 lakhs or maybe 80 lakhs or whatever, 50 lakhs or something like that. So this will be the market sale price. So now when it comes to terminology, you will see that the samples which we take, this is house number 1, 2, 3. These are all what we call as the observations. And then we have these things which, the pricing of houses depends on the neighborhood, depends on the area, depends on the bedrooms. So these are examples of features, which we also call as, the dimensions or attributes. And then these are the target, that what is the final answer, that hey, okay, this is the house which is in this locality, this much is the area, these many bedrooms, and this is the price for that house. So these are your target variables. And what are we trying to do via this? We are trying to predict that if I now give you a new house, house number 100, which is in certain neighborhood, certain area and certain bedrooms, can you predict what price is a good selling price for that house? So this is a very simple example of the different terminologies. So targets, features, and observations. These are the main terminologies which we use. So now let's see what a model is. What is an ML model? So please remember this information from here, observations, features, and targets. And let's take a look at what a model is. So model is an approximation of the relationship between two variables. So for example, if you have input variables x over here, so model is something which is a function of x plus epsilon. So epsilon is just, just a constant. So you can sort of ignore it for now. But basically it adjusts for any constant values. But in essence, a model is nothing but just a function applied on this variable. So if you may remember when we were kids, we used to learn about functions, right? Some functions are linear, some functions are quadratic, some functions are exponential. So based on, how much you increase x, how much is y going to change its behavior. So this is in essence what a model is just a relationship between two variables. So yeah, so this is just a visual representation of it, that if you have input variables over here, like horsepower, 75, 100, 125, or 150, blah, blah, and this is the output variable. So you can plot it like this, and then you can get the curve. So this curve is in essence how the ML model is sort of represented graphically. Okay, so how do we build an ML model? So there are three, four things which you should know about a model. Firstly, there are the features. So you remember we talked about the features over here. These are my features: neighborhood, square footage, bedrooms, blah, blah, blah. So features are the parameters on which my house price depends on, like area, bedrooms, blah, blah. The algorithm is like, a template for the model. So you remember how we talked about that this relationship between y and x can be linear, can be quadratic, can be exponential, or many of those other kinds of functions which we have. So this is what we mean by an algorithm. That is the relationship, linear, quadratic, or what is it? So then we have the algorithm, then we have the hyperparameter. So hyperparameter are kind of like, knobs, you can say, which you can increase or decrease to sort of fine tune your algorithm. So we'll learn about that in a short while. And loss function is the one which you try to optimize. So by loss function, what we mean is that, for example, if I predict that a house with this much area and this many bedrooms has a price of $500,000, that is my prediction. But in reality, the price is $600,000. So my loss function is going to be the difference, that, hey, okay, I predicted something to have value 500, but its actual value was 600. So then my loss function is, the subtraction of both of these, and I now try to optimize for that. So in any ML model, we always try to optimize the loss function so that our ML model predicts things as accurately as possible. So we train our model using historical data, algorithm and hyperparameters provide the model, and then it learns the value from the model and minimizes the loss function. So these are the three, four main things in an ML model. So, okay, so now let's see what are the different types of machine learning. So there are three main categories: supervised, unsupervised, and reinforcement learning. So by supervised learning, we mean that we want to predict, a target variable. And the main difference is that it is always done on pre-labeled data. That is, you give it 1,000 pictures of animals and you give it labels that, hey, okay, this is a cat, this is a dog, this is a horse, this is squirrel, whatever. So you have those answers already. So that is an example of supervised learning. So an example for this is, classification and regression algorithms. We'll learn about them in a while. But like real life examples is that if I am a doctor, I am a radiologist, and I am seeing the MRI scans of your lungs, and I have 1,000 such lung scans, and I know which one of them were the ones which were having cancer. So now if you give me a new sample besides those 1,000 older samples, machine learning algorithm can sort of predict, that whether this particular lung sample is going to have, cancer or pneumonia or whatever. And I'm predicting real estate prices as well. So you already have historical data that, oh, okay, these are 1 million homes in Bangalore or whatever, 10,000 homes in Bangalore, and these are, the prices of these homes. So we already have that label data. So that is an example of supervised learning. Whereas sometimes you may not even have the label at all, and you just need to, find mysterious patterns in the data. So for example, if I make an app, if I make a gaming app, okay, and I need to find out, what is, the persona of my customer who most frequently uses my gaming app. So that is an example of, trying to identify user segments that I don't really know right now. Maybe teenagers are using my gaming app. Maybe people between ages 18 to 35 are using it. Maybe a bit middle-aged people are using it. Maybe females are using it less than the males. It can be anything. Like, I don't even know what it's going to be. So that is an example of unsupervised learning, where you don't even have the labels in the data, but still you need to find some patterns in it. So, clustering and anomaly detection are examples of this. So by clustering, we means that, okay, these are the users which all show similar kinds of behaviors. These are the users which all show similar kinds of behaviors on other aspects. So that is unsupervised. And then you have reinforcement learning, where you teach an ML model that, hey, okay, it is the most commonly used, in robotics and in autonomous vehicles, where if the robot takes if you instruct the robot with something and it performs everything correctly, then you reward it by giving it some points, something like that. Whereas if the robot takes a wrong step, then you kind of like, deduct its points, or you sort of like, punish it in some way, you can say. So reinforcement learning is more that if you do a good thing, you will be rewarded. If you do a bad thing, you will have to pay for it. So this is how robots are generally trained. And this is reinforcement learning is very commonly used in autonomous vehicles, where your objective is to achieve a goal. So these are the three main types of machine learning. Okay, so now coming to supervised and unsupervised learning. So you can just take a look at this, image over here. You have these images of different fruits, okay? And then these fruits are labeled as apple. These are apples. You feed it 1,000 images of these fruits and these 1,000 labels that this is apple, this is mango, this is blah, blah, blah. So then if you now give it this particular image, okay, then the model will predict that, hey, it's an apple. So this is a supervised kind of a machine learning, where you have images and also you have their labels slash annotations. Whereas in unsupervised learning, you give it large number of fruits and there is no label. Like, machine doesn't know that this is an apple, or this is a tomato, or this is a banana, or whatever. Machine doesn't know anything at all. Then now if you give it to the machine, what it will do is that it will just segment and divide it into fruits which are of the similar categories. So all the apples will be in one group, all the tomatoes will be in one particular cluster, all the bananas will be in one particular cluster. So this is where the clustering is happening. And if you remember, we saw that clustering is an example of unsupervised learning. Whereas in here, you were training it on apples and its annotations, you were giving it a new apple and you were predicting it. So this is a sort of an example of classification, where you are sort of giving it a new image and now asking it to categorize it into an apple or mango or whatever. Okay, now coming to regression versus classification. So in regression, we sort of predict one or more numerical target variable. For example, temperature, or prices of the houses, or how much power is going to be used in a factory or in a city, that kind of thing. And then you have a classification, where you predict that, hey, okay, is this MRI sample of the lung, is it pneumonia or cancer positive, or is it pneumonia or cancer negative? Or if I give you a collection of reviews on Amazon for a product, then is this review a happy review that the user is happy, or is this an unhappy review that the user is unhappy with you? So this is an example of classification, where your data is going to fall into two or more categories. So here you have categories or classification, and here you have a continuous values which your target can attain. That is the regression. Okay, so let's see what ML can and cannot do well. So these are the things ML can do well, that is automate straightforward tasks and make predictions and personalize for individual users. But this point is very important, star marked, given sufficient quantity and quality of data. So for example, if in your product you have 100 users only, and now like your product has 100 users only, and now you think that, hey, okay, let me develop a recommendation algorithm over it. Well, I would not advise that you do that, because 100 is very less sample size for, in general, for ML based recommendation algorithms. So till the time you have at least, 10,000 or 100,000 samples, before that you shouldn't use ML at all. So that is a problem which many startups will run into, that they forcefully want to use ML, but they don't even have data, and that, or that data is of bad quality. There are missing fields everywhere. It's all jumbled up or inaccurate. So in those cases you should not use ML, but at the same time it can help you make very good predictions and personalize. What ML cannot do well: ML cannot understand context that well. ML cannot determine causation, that what caused this particular thing. It can explain you the behavior, that hey, this is how, sort of, it can explain you the how of the things, that hey, okay, this is how the universe is expanding or whatever, and this is where it will be 100 billion years from now. But it cannot tell you that why the universe is expanding or why the big bang took place. Oh well, that is very difficult for ML to predict that. So, and then it cannot determine the impact of interventions or find solutions. So if I say that, hey, okay, climate change is happening, there's a lot of global warming, blah, blah. So now, if I try to make any interventions over it, then machine learning cannot sort of suggest to me, the impact of all those interventions, or be able to find solutions for it. Whereas when it comes to automating simple tasks and for personalizations, ML can do that really well. So these are just some of the examples where you should and should not use ML. Okay, so now let's see what the modeling process looks like. So, modeling process is very much iterative, and this whole chain and this whole cycle you will have to repeat again and again till your ML model performs at, according to the level of accuracy you want it to perform. So you remember how we were trying to predict the prices of in real estate or prices of homes. So in that, first of all, you select features. But my features are: what is the area of the home, which neighborhood is it in, how many bedrooms it has, how old it is. So these are examples of features. So first you select the features, then you sort of choose the algorithm. So if you remember, we talked about how, in math, the different functions can be linear, quadratic, exponential. So then you choose the algorithm, that, hey, okay, is this model you're going to use, does it necessarily, follow a linear relationship? So in here, you choose the algorithm. It can be regression, classification, anything else. Then you set the hyperparameters. That is, you define how fine tune you want your algorithm to be. Then you sort of train your model, that is, you train it to sort of predict any new values. And then you take a testing sample and you test it on that sample data, and you try to see that for how many of these testing samples did it predict correctly or not. And then if you feel that, hey, okay, it is predicting correctly only for 70% of the cases, but you want it to predict accurately for at least 90%, then you sort of repeat this whole process again, where you select your features again. Maybe you think I should choose a different algorithm this time. Maybe you choose the hyperparameters differently, and so on. So you just keep repeating this cycle iteratively till you attain the required amount of accuracy. Okay, so this we have seen earlier, just about the features, and we are taking again this real estate prices example in here again. Okay, so now let's take a look at the underfitting versus overfitting versus a good fit. So for example, if you have an underfitting like this, So if you take a look at this, this light blue line is my model. Okay, so my model is predicting that these values are going to fall on this particular line. Whereas my true function, or you can say the samples, which are, these dark blue dots. So these are, the real values that, hey, okay, for this particular X value, this was the Y which was really there. But my algorithm predicted the one in the light blue one. So this is an example of underfitting where my model is too simple. I'm predicting that everything is linear, whereas that's not really true because my true function looks something like this curvy line over here. Whereas now if you take a look at this overfitting kind of an example, in this what is happening is that it is being very strict and tight on all the sample values. So these are my real sample values, and it's saying that, hey, okay, this function first starts from here, then it goes here, then here, then here. So it's all like very tightly fitting. So the problem with overfitting is that it sort of memorizes the data which you run it on. That if you give it 1,000 samples, so it's as if like when we were kids, sometimes we would just learn math equations just like without understanding them. But now if you give me a totally new math problem, then maybe I won't be able to solve it because I didn't really understand it very well and I sort of just memorized it. So that is an example of overfitting. So doing this is also bad, and doing this is bad as well. Whereas if you take a look at this good fit, you will see that in here the model fits well, but there is only some error. So this line is sort of nearly coincides with all my true functions with only small variations in it. So this is underfitting, overfitting, and good fit. Okay, so I think we just have 5 minutes, so I'm just going to make it a little bit quick. So we'll see a linear regression. So we saw earlier that X and Y may have a linear relationship between the features and the targets. So this is what we call as a linear regression. And remember, the values in here are continuous and not categorical. So this is an example of a regression algorithm. So why do we use linear regression? Because it is one of the very simplest models, and it is often used to sort of get like a very basic benchmark, or that, hey, okay, using linear regression, you got an accuracy of 85%. So now in the future, when you try to optimize, you should ensure that your accuracy is greater than equal to 85% at least. So that's why it's most commonly used. And then in logistic regression, logistic regression is used in sort of classification problem. So for example, if you want to predict a class having a value 0 or 1, so if you are doing a sentiment analysis and you want to predict whether this review by the user is positive or negative, then that is an example of a classification problem. So you see all the Y values here are either in this particular area or in this particular area. And then we have decision trees. So in decision trees, what happens is that you ask a series of questions and narrow down on the label. So let's take a quick example over here. So you ask, if I give you this particular sample data, that, hey, okay, this is animal 1, this is animal 2. They have horns, this is the color, this is the number of legs, and these are the labels. So you ask, okay, is my new animal having horns? No. If it does have horns, then it means that it's a moose. Then how many legs does it have? If it has 2 legs, then it's a bird. If it has 4, then okay, we need to ask more questions. Then finally you ask what color it is, and based on it you predict what animal it really was. So I think I'm just going to skip this over because we're sort of running short of time. And then let's just see what deep learning is. So right now if you can say that ML is kind of like how you teach machines to learn on their own. Neural networks are kind of like fashioned on how human brain works. So human brain, you can consider, has thousands and millions of layers, and all those layers are constantly communicating with each other in a backward and forward loops. So that is the structural model of a neural network, and this is generally used for more advanced ML problems. Okay, so when to use deep learning? It is generally used when you have very large amount of training data and when you have a lot of unstructured data and where the relationship between the features and target is very complex and where you don't need to explain your reasoning much. So there is sort of, less explainability. So for example, if you want to predict the weather, now weather has like, thousands of really unpredictable variables like, pressure and humidity and all those kind of things. So that is a very complex system, but still if you want to predict what the weather is going to be like and you don't really need to explain how you arrived at that conclusion, then this is very well you can use neural networks where you don't need to explain your reasoning. So let's take a quick example of common NLP tasks. So text classification, sentiment analysis, searching, machine translation, and text generation are some of the common NLP tasks. So, for example, when you work with text, so you follow, there are multiple ways to sort of represent text for modeling. You can represent them as a bag of words, or where you define that, hey, okay, these are the words which are there in all my sentences, and this is the frequency with which they are occurring. Or second is where you use word embeddings, and lastly is where you use attention or transformers. So I think we are running short of time. So I will take a pause now and we can take it up sometime in the future if we get a chance. So for now, I will hand it back to Pratap now.
Yeah, that was a great session, Shreya. So we have some questions regarding this non-coders guide to the machine learning.
Mhm.
So one of the women is asking about the what is the importance of data in machine learning? How does the data quality impact on the model performance?
Can you please repeat the second line? How does the data quality?
Impact on model performance.
Oh yeah, yeah. So I think like our data is like really very important for machine learning and AI because like you are not writing a specific algorithm. You are not writing in it in a traditional way using if else loops or a conditional or something like that. So the only source of truth for any AI or ML algorithm is the data itself. So you first of all need large amount of data. Like taking a data sample size of 10 or 100 is not going to be useful. So first of all you need to ensure that you have a very large amount of data, substantial one. I would say at least greater than for all for example for recommendation engines you need to take at least 10,000 at least, although even with 10,000 it may not work that great, so 100,000 is preferred, but that can be a starting point. And then when it comes to quality, so if you really have bad quality of data, that you have a lot of fields which are missing, or a lot of fields which are not, some things, some bad quality of the data can be solved. Like, and that is what we do, when we clean the data, we sort of make it more in a uniform format, and we try to sort of extrapolate and fill in the missing values. But if the data quality is bad, that is a lot of things are missing, things are very improper, and sometimes different tools are going to have conflicting data. Like in one software you have that this person belongs to India, but in other software you have that this person belongs to somewhere else. So these are all conflicting kinds of data. So in these kind of situations it really directly affects the performance of your AI/ML model, and it would be very risky to use AI/ML model then.
Yeah, yeah. And
Mhm.
one more question from the other person, like how can a model catalog help ensure a transparency and accountability in the like machine learning projects?
Can you please come again? Can you please repeat that?
How can a model catalog help ensure transparency and accountability in machine learning projects?
Okay, so like for some cases, that's what we you talked about. We talked about 5 minutes back about the explainability. So, in some cases,
yeah,
ML models need to be explainable, whereas in some cases, they don't necessarily need to be explainable. So, for example, if you're a doctor and you're predicting that a certain person has some serious, illness, like some cancer or something. So, in that case, you perhaps need to give a logic that, hey, okay, this is the reason why we are predicting that something is happening. So, I would say that the places where you need to be responsible for your customers, or you need to be responsible and accountable for certain things, in those cases explainability is very, very important. Whereas if you are the product manager at Netflix and you are giving recommendations of which movies to watch, well, maybe explainability is not that much needed, because no one is going to come and ask answers from you that, hey, okay, why did you recommend me this movie and not that? Because that is like not a very high stakes problem. So therefore, this is where that the transparency part which you asked about, that comes into picture. And wherever explainability is needed, you should use different kinds of ML models which are more, you can say, interpretable. Whereas in others where the stakes are a bit less, you can use more like black box algorithms or maybe neural networks, those kind of things.
yes, 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 of course. And one more, the final question for you is explain the concept of prompt flows and their role in enhancing the utility and accessibility to learn LLM.
Can you please come again? I am not able to hear you properly.
Okay, so explain the concept of prompt flows and their role in enhancing their utility and accessibility of large language models.
Okay, so I think the LLMs are used on more like the attention and the sort of the transformers model. So I would say, like in basic essence, how they work is that, like, if for let's take a step back and first take a look at, like, how the embeddings work and stuff like that. So, like, for example, if I give you a
Yes, yes,
word,
of
if
course.
yeah, so if I give you, like, for example, if I give you a word such as, a cat sits on the blank, and now you need to predict what that blank is. So that blank can be, the cat sits on the mat, or the cat sits on the cloud, or there can be a thousand other things. So it will kind of like figure out that, hey, okay, out of all the sentences which it has so far encountered, the the word mat and cat are very closely related to each other, whereas maybe the word cloud and cat are sort of less related to each other. So that is in essence, how you can say, this whole thing works. And it those word embeddings are also sort of useful when you need to sort of categorize words which co-occur, or occur near to each other. And then when we move on to the transformers model, so how we do it is that you sort of, if you have a sentence, so each of the words in those sentence has a weight, and it is related to other words in that particular sentence. So that is how, and it's not very simple for me to explain, without like some graphical demonstrations, but that's like the basic essence of it. And in essence, I wouldn't say that I am very expert, in LLMs as of now, because that is relatively a new technology. So I wouldn't be able to comment on, the intricacies of it. But yeah, I think that's like the general overview of how it works. I think you're on mute, Pratap. You went on mute.
Sorry, yeah, sorry, sir. Yeah,
Mhm.
that makes sense. So actually, the prompt, prompt flows and the model catalogs, and these are the lot of the, I mean, new features that will be added into the machine learning that plays a key role in the enhancing and enhancing the future of this machine learning and everything that will be possible with these new technologies. That too, Microsoft launching, I mean, every new updates to this machine learning models and Azure AI models. I don't know
Yeah.
exactly. I think the some of the new features, some, yeah, yeah. So some model catalog models are so similar in the machine learning platform and as well as the Azure AI Studio as well. So
Yes.
yeah, that's pretty cool. Sometimes I'm using this Azure AI Studio as well as the machine learning
Hmm.
as well. Yeah.
Okay. Okay.
So yeah, thank you. Yeah, yeah. Thank you so much, Aishwarya, for your valuable time to give in the session for our audience. And so
Hmm.
there, I mean, I got some lot of responses.
Mm-hmm.
in the Discord as well as the Facebook as well. And
Okay.
probably I can tag you in the meanwhile. So because I need to shift to the another call. So thank you
Sure,
so much,
sure.
Aishwarya. Yeah, thank you so much for
Okay,
your
then. Thank you so much for inviting me. And
yeah,
thanks,
and
everyone. Bye
and
bye.
bye. Yeah.